The next section we'll look at is section 2.5 on the real numbers. The set of real numbers consists of the union of the rational numbers and the irrational numbers. So notice a brief typo here. This should read rational numbers. So a real numbers, if you're kind of breaking it up into sets, can fall into one of two categories. Either a rational number, namely those whose decimal expansion either terminates or whose decimal expansion repeats, and the collection of irrational numbers, which are the numbers whose decimal expansion does not stop as well as it does not repeat. We've already seen a few distinct subsets of the real numbers. Namely, we started with the natural numbers, which are sometimes also referred to as the counting numbers. Those are the numbers 1, 2, 3, 4, 5, etc. We talked about the whole numbers, which also include 0. So it's 0, 1, 2, 3, 4, 5, etc. Again, an easy way to distinguish between the natural and the whole numbers. They're very nearly the same set. The only difference is the whole numbers includes 0, whereas the natural numbers does not. Again, if you look at the word whole, kind of like the letter O, kind of resembles like a 0. So 0 is in the whole numbers. 0 is not in the natural numbers. From there, we moved on to the set of integers. The integers are the whole numbers and their negatives. So 0, 1, 2, 3, 4, etc., as well as -1, -2, -3, etc. We talked about the set of rational numbers in terms of their decimal expansion, but when we define them, we said that the rational numbers are those that can be written as a fraction, where a and b are integers. So if you can write the number as a fraction, then it's a rational number. So things like a half. The mixed number 3/4 we know is equivalent to the improper fraction 13/4. A terminating decimal or a repeating decimal, so something like 0.3 repeating, we know is equivalent to 1/3. The terminating decimal 0.6 is equivalent to 3/5. Or even our integers, which you can think of as being over top of 1, would all be examples of rational numbers. So to be a rational number, oftentimes it can be difficult or a little bit time consuming to have to write it as a fraction. You can also just look at the decimal expansion for a number, and if it stops or if it has a repeating block, then it's rational. Some examples of irrational numbers we talked about are like pi, 3.1415, it doesn't stop, it doesn't repeat, or any type of square root which doesn't break down perfectly, like the square root of 2 or the square root of 5. Those also have infinite decimal expansions that don't repeat. Let's take a look at example 1. We are given a set, and we want to classify the different types of numbers within that set. The first one we're asked to classify is which of these would be the natural numbers. And before doing so, one of the things that I noticed, if I'm looking at the set, be a little bit careful here. That square root of 81, we know that that's actually equal to 9. And that may play a part whenever we try to list these things. First of all, the natural numbers are like the counting numbers. So 1, 2, 3, 4, etc. The only number in that list that would be natural would be the square root of 81, because we know that that's equivalent to 9. The whole numbers, again, would include 0, 1, 2, 3, 4, etc. The only number in that list that would be a whole number is again going to be the square root of 81. The integers are the whole numbers and their negatives. So that would include now -7, which is a negative whole number, as well as the square root of 81. The rational numbers would be any number that we can write as a fraction or a ratio. These include the integers, so that would be -7, -3/4, 0.6 repeating. Remember, if it has a repeating, then that makes it rational. The square root of 7, if you're unsure, you can plug it into your calculator. But the square root of 7 maybe I can plug it into my calculator. If I turn it on, well, it's not going to cooperate. But I'll leave it up to you to reason through. But square root of 7, it's not going to have a repeating decimal expansion, right? That's one of those square roots that does not break down, so that's not going to count. Same thing with pi. We know that that's irrational. 7.4 has a decimal part that stops. And then again, the whole number, the integer 81 square root, would be an irrational number. The irrational numbers in the set are the ones that don't stop and don't repeat. That's going to be square root of 7 and pi. And then lastly, which one of these are real numbers? All of them. So every single number in this list is going to be a real number. Some of the properties we have for real numbers are what's referred to as the associative property of addition and multiplication. And this says that if you have three numbers and you're adding them, a plus b plus c, you can add the first two and then add the last one, or you can instead add the last two to the first one. So you can associate the addition. You can start by adding any two that are next to each other. Likewise, whenever we have the associative property of multiplication, this would say that if you have the product a times b times c, you can multiply a times b first, get that answer, and then multiply it to c. Or you could do the b times the c first, because they're side by side, and then take that result and multiply it by a. We also have the commutative property of addition, which says if we take two numbers, we can add them in any order, we're going to get the same result. So we know that 2 plus 7 equals to 9, and it's the same answer we get if we did 7 plus 2, would also equal to 9. Multiplication is also commutative. If I do 2 times 7, that gives us 14. We also get 14 by doing 7 times 2. Notice that the two operations that are not listed here are subtraction and division. Subtraction and division are not commutative. For example, if you do 7 minus 2, that would give us 5, but 2 minus 7 would give us negative 5. So with subtraction, the order matters. You can't change the order around and get the same answer. Same thing with division. We did talk about this in class one day, but if you do 4 divided by 2, that would give us 2, but 2 divided by 4 would equal to a half, which is 0.5. So with addition and multiplication, you can flip the numbers around and you get the same answer, but so those two operations are commutative, but subtraction and division would not be commutative. We also have the distributive property, which describes the way in which multiplication interacts with addition and subtraction. If we're taking a number times a sum, it's the same thing as the sum of the product of the number with each of those. So we would take a times b, take the a times the first value in the parenthesis, and then add to it a times the second number in the parenthesis. It works the same way for subtraction. A times b minus c, we distribute the a in, and that would produce ab minus ac. We have a few special properties of addition, namely the additive identity for addition is 0. What that means is if you take 0 and add it to any number, it leaves the number unchanged. So for example, 7 plus 0 we know is still going to be 7. Likewise, if I do 0 plus 7, that still gives us 7. So adding by 0 does not change the result. So that's called the additive identity for addition. We also have an additive identity for multiplication, and this time it's going to be the number 1. You can take the number 1 and multiply it to any number, and it will leave the number the same. So 1 times 7 is 7. Likewise, 7 times 1 is still going to be 7. We have what's referred to as the additive property of addition, the inverse additive property, which says that if you take any number and you add its opposite to it, that's going to result in 0. The additive inverse of any number is that number's opposite. So the additive inverse of 5 would be negative 5. Similarly, the additive inverse of negative 5 would be positive 5. If you take 5 plus negative 5, or if you do negative 5 plus positive 5, both of these result in the additive identity 0. And so we would say that those two numbers, 5 and negative 5, are additive inverses of each other. For addition, it's very simple to find the additive inverse. All you're doing is finding the opposite of the number. We also have an inverse property of multiplication. If you have a real number that's different from 0, you can find its multiplicative inverse by doing the reciprocal. And what happens is if you take a number and you multiply it by its reciprocal, that gives us the multiplicative identity 1. So for example, if I think of, let's say, the fraction 3/4, the reciprocal of 3/4 would be 4/3. You're just taking it and flipping it upside down. And if I take 3/4 times 4/3, this ends up giving us 1, because you get 12 over 12, and 12 goes into 12 once. Or if I did 4/3 times 3/4, that also gives us 1. For instance, if you wanted the multiplicative reciprocal of 2, you can think of 2 as like 2 over 1. So if you reciprocate that, you would get 1/2. So 2 and 1/2 would be multiplicative inverses of each other. In example 1, we're asked to identify the property illustrated in each calculation. We have addition. It says that 6 plus 5 is the same thing as 5 plus 6. That would be the commutative property of addition. Commutative property says you can do the operation in any order. 6 plus 5 is the same thing as 5 plus 6. If you look at F, let's kind of jump around a little bit. That essentially is saying the same thing, but as it pertains to multiplication. So in F, this would be an example of the commutative property, but for multiplication. In part B, I'm multiplying 2/5 and 5/2, and I'm getting 1. That would be the inverse property of multiplication. Multiplying a number by its inverse produces 1. In part C, this would be the additive identity property for 0. Remember, additive identity says that if you add 0 to anything, it leaves the number unchanged. So this is the additive identity property. Now let's take a look at D. Here, D says that 6 times 7 multiplied to 3 is the same thing as 6 multiplied to 7 times 3. And the use of the parentheses is associating or grouping a set of numbers within each multiplication. So when we rearrange that grouping, 6 times 7 as opposed to 7 times 3, this is going to be the associative property for multiplication. The last one we have to cover is E. We have 4 times 3 plus 9. They're claiming that this is equal to 12 plus 36. Well, where is that coming from? Notice that they're taking each number in the parenthesis and multiplying it by 4. 4 times 3 gives us 12. 4 times 9 gives us 36. So they're distributing the 4 in, so E would be the distributive property.